Hi class, today we're going to talk about electronegativity, character of bonds, and overall polarity of molecules. Here you'll see there is a whole table of electronegativities we'll refer back to a few times throughout this lesson. The other thing that we're going to be looking at is our VSEPR diagram, so our shapes that we have made. So we have got 2 bonding areas, 3 bonding areas, 4 bonding areas, and that's about as many bonding areas as we'll go over today. Today our goal is to discuss, once again, the polarity of overall molecules, and to do that we need to understand the character of different bonds, meaning are they nonpolar bonds, are they polar bonds, or are they ionic bonds? And then we're also going to look at electronegativity to help us with that. So once again, this is a table of electronegativity. You guys had this on your worksheet from yesterday. So we'll just go ahead and get started. Now that we're going to, hold on one sec. Now we're going to look at the polarity of the molecules we have drawn out. So on your homework from Monday or Tuesday, you drew out a whole bunch of different molecules using Lewis structures. So we're going to look at, once again, the overall polarity of the whole things. We do this once again by looking at the electronegativity of the atoms involved, the differences in electronegativity, and then determining if the overall molecule is polar or nonpolar. So the first question is, what is electronegativity? Electronegativity is the atom's ability to attract electrons. You should have that on your sheet from the other day, but just a reminder, electronegativity is the atom's ability to attract electrons. So the higher the electronegativity, the more atoms are able to attract electrons. So for example, if we look at this chart again, we see that fluorine is the most electronegative, meaning it really attracts electrons, versus francium, which is all the way down here, francium and cesium, have the lowest electronegativities, meaning they don't attract electrons very well at all. You'll notice that the noble gases have 0 electronegativity because, remember, they're pretty stable where they are. They have those 8 electrons, so they're not really hunting for any more electrons. So what we do when we look at this, the first thing we do is draw out the molecule. So carbon with 4 hydrogens is going to give us this shape. So now that we have our shape, we want to use this shape. We want to figure out the differences in electronegativity. How I draw out electronegativity is I use arrows. In your book it talked about partial positives and partial negatives. I put the positive side down here, and then I know that this end of the arrow is negative. So in your text talked about partial positives, meaning there are less electrons down here, and the partial negatives, meaning the electrons are hanging out more down here, the electronegativity is greater down here. This is the shape I draw. If I go back to that original chart and I look at the electronegativity differences between hydrogen and carbon, I'll see hold on. That hydrogen has an electronegativity of 2.2, carbon has an electronegativity of 2.5, so I know that carbon is more electronegative than hydrogen. Therefore, I'm going to draw my arrows pointing towards carbon, the more negative one. So I just go ahead, I'll use a different color so you can see it. Use blue. I know my partial positive is this way, and my negative towards the center. Once again, partial positive on the hydrogen, my negative more towards the center, because remember, carbon is more electronegative than hydrogen. Once I do that, I kind of take a step back, and I look at this molecule, and I say, is that polar or nonpolar? Before we talk about if something's polar or nonpolar, we kind of have to understand those ideas. So here are some notes on those different ideas. If we're talking about something being nonpolar, we know there's no pull of negativity overall, or no electron pull overall. we know that if we have symmetrical pulling arrows, so arrows pulling all in the same direction, either if that's out or if that's in, there's an equal pull across the whole molecule, and that leads to a nonpolar molecule. When we have an asymmetrical pulling of arrows, or the negative is pulling one way, we call that molecule polar. So symmetrical molecules with polar bonds are not polar overall. The partial charges are balanced, and there is no one end of the molecule that has a different charge than another end. They can be nonpolar molecules. That was a question, I think, on your worksheet too. It was talking about can polar bonds occur within a nonpolar molecule, and yes, they definitely can. Asymmetrical molecules are with polar bonds are still polar overall. There's one other thing I did want to tell you about. Let me see if I can find that. Okay, here we are. So when we look at the electronegativity of these atoms and the changes of electronegativity in these atoms, we are trying to identify what types of bonds are they, and we can do that by looking at the change in electronegativity, or this delta En, so the change in electronegativity, and we find, are these bonds nonpolar, are they polar, covalent, very polar, mostly ionic, or very ionic? And that ranges from 0 to 4, the change in electronegativity. If it's between 0 and 0.4, we say that they're nonpolar bonds. If it's between 0.4 and 1.7, we say that they are polar bonds. If it's between 1.7 and 4, we say they are ionic bonds. So let's go back to that first example that we were kind of working through. We looked at the difference between carbon and hydrogen. There's two ways to characterize these elements. There's the overall bonding within the whole element, and there's the individual bonds. So I could ask about the bond character between this hydrogen and carbon, and that would be asking, what type of bond do I have? So if you remember from that other page, I'll show you again. Carbon had an electronegativity of 2.5. Hydrogen had an electronegativity of 2.2. So the difference would be 2.5 minus our 2.2. That doesn't look like a minus. Gives us 0.3. If we go back to that chart, we can see that 0.3 is nonpolar. So we know that the bonds within the molecule are nonpolar. We want to know, is the overall molecule nonpolar or polar? We go back to this picture, we see that the arrows are all going in the same direction, so there's an equal pull across the whole molecule, so we're going to say that that is nonpolar. So we'll say the C to H bond is nonpolar. Nonpolar. And the CH4 molecule is also non-polar. Alright, let's try this a couple more times. So now let's look at this molecule NH3. Let me draw the Lewis structure quick. I'll be right back. Alright, here's our NH3 molecule. Once again, we're going to look at the bonds between nitrogen and hydrogen like we did for that carbon-hydrogen to find the bond character, and then we're also going to look at the polarity of the overall molecule. So let's say bond character is, let's look it up. So we need nitrogen and hydrogen. So we have hydrogen still, right? Now I gotta look up nitrogen. So nitrogen is 3.07. So we'll take our 3.07, take away 2.2, and we'll get 0.87. So now we want to use the our little chart on that other slide to tell us, we said it was 0.87, right? Yep, 0.87. So that 0.87 our change in electronegativity is 0.87, so that's going to be right here. We're going to say that that's a polar covalent bond. So our bond character for this molecule, we're just up a little high on the slide, the bond character for N to H is polar. Now we want to talk about the overall molecule. So the molecule, let's look. So we just said NH is polar. We know N is a lot more electronegative than hydrogen. So we're going to draw our little arrows, and remember we want our arrow to go towards the more electronegative thing and our positive part to be towards our less electronegative thing. So here is one of our arrows, another one, and our third arrow. Overall, it looks like this would be a polar or a nonpolar molecule, but an important thing to note is that if I have electrons, a lone pair of electrons, that is a lot more electronegative than the nitrogen itself. So we're going to make an arrow upwards towards the electrons, with the bottom being on the nitrogen, because electrons are more electronegative than the nitrogen atom. So as you can see, we have 3 going towards the nitrogen and we have 1 going straight up. So would you consider that symmetrical or asymmetrical? I hope you're thinking that's asymmetrical, because we've got 3 things going one way, 1 thing going out. So our whole molecule overall is going to be polar. I would like you guys to look at these next 2, carbon dioxide and water. Try to do those and then check your answers. I'll just write the answers here in a minute. Here are your answers to those 2 questions. So double check your answers, see how you're doing. Remember, we want to draw the molecules out. We want to figure out the electronegativities of each number, figure out the change in electronegativity, look at our chart down here, and figure out if we have a non-polar, remember 0 to 0.4, a polar 0.4 to 1.7, or an ionic 0.7 to 4. Then we're going to talk about the character of specific bonds, and then the polarity of the molecule overall. We want to make sure that as we're working through these problems, we are paying close attention to our changes in electronegativity and the way that our arrows are facing. What I would like you to do for Friday, you need to, number 1, write in your bonding character for molecules on that same worksheet that we've been working through. So on that Lewis structure worksheet. The second thing I want you to do is write in, or determine if the molecule is polar or nonpolar for each of those molecules. On Friday, we are going to review those ideas together, and then we'll also work through another practice worksheet. So Friday, we'll work through a practice worksheet, kind of practicing all of these ideas. We're also going to talk about why polar and nonpolar don't mix. Monday, we will review. Remember, next Tuesday, then, we have our quiz. I hope you guys are having a great day, and I'll see you tomorrow. Bye.